morning, students. In today's class we shall study about differentiable functions. So let's first start with the definition. A real valued function y is equal to fx is said to be differentiable at some point x is equal to a, which is a point in its domain, so a function is said to be differentiable at x is equal to a if limit of fx minus fa upon x minus a when x tends to a finitely exists. It has to exist, then it has to exist finitely. That means this limit should be a real number. Now, since we are mentioning here that this limit exists, we know from our previous knowledge that limit will exist if the left hand limit is equal to right hand limit. So let us write down the left hand limit, and we know symbolically we write down like this: x tends to a minus fx minus fa upon x minus a. This should be equal to the right hand limit, which is written like this. So here you can see this minus and plus sign indicates that we have written here the left hand limit and the right hand limit. Here we know that x will tend to a minus h if h tends to 0. So changing the limiting point to 0, this equation can also be written as limit h tends to 0 f of, now in place of x, let's write down a minus h. Denominator x is a minus h minus a. This is the left hand limit we have written. Similarly, on the right hand side, x will tend to a plus h if h tends to 0. So once again, changing the limiting point to 0 and replacing x by a plus h, we get this expression. Okay, so here this is basically limit only, the left hand limit and the right hand limit. You can see here that the denominator can further be simplified. So on simplification, we get an expression of this kind. Denominator here is minus h, and on the right hand side, f of a plus h minus fa upon h. This is what we are getting. So this is basically the definition of a differentiable function. So whenever these two limits are equal, that means these two limits are equal, the function will be said to be differentiable at the point A. So what you see here on the left hand side is an expression which now we shall be calling left hand derivative. In short, LHD. Likewise here, this is the right hand derivative, and in short this is written as RHD. So whenever the left hand derivative is equal to the right hand derivative, the function is differentiable at the point x is equal to a. Although these are limits only, but now we shall be calling them left hand derivative or the right hand derivative. If you have a closer look at the right hand derivative, this one, this is what we have referred to as first principle of derivatives in previous classes. And using this first principle of derivatives, we had basically derived the derivative results of various functions. That means when we differentiate functions, what should be the result that we get? That was obtained using the first principle of derivatives, which now we have seen is basically the right hand derivative. So once again, whenever LHD is equal to RHD, the function is said to be differentiable at x is equal to a. So that means we can find out here derivative of y. So symbolically, derivative of y can be written like this. We read it as y dash. It can also be written as like this. This is y1, 1 is the subscript. We can also write it down as dy by dx, where we know y is the dependent variable and x is the independent variable. So the dependent variable is differentiated with respect to independent variable. Now y can also be represented by fx. So if we want to write down derivative of fx, we can write it down as f dash x. We can also write it down as d by dx of f dash of fx. Okay, these are ways of writing down the derivatives. If we want to find out here derivative, say at some point x is equal to a, then how can we write down the derivative? If you are writing this way, we can write down y dash at x is equal to a, y1 at x is equal to a. We can write down here dy by dx at x is equal to a. If you are writing it in this format, we can write down it is f dash at x is equal to a or f dash a. So these are various ways of writing down the derivatives of the function. So now since we have seen the LHD and RHD, and we know that whenever LHD is equal to RHD, the function is said to be differentiable. What exactly do we mean geometrically when we say that a function is differentiable? That's what we are going to see next. So next, let us see here the geometrical significance or interpretation of differentiable functions. We can also say geometrical interpretation of derivative of a function. So for this we need to draw a graph. So we'll draw a graph of a function in the first quadrant. It can be drawn anywhere. For convenience sake, it's being drawn in the first quadrant. So this is the curve of some function y is equal to fx. On this curve, let us take a point P, and this point P corresponds to a point A on the x-axis. So here I am going to write down coordinates of the point P. It is A, FA. Now on the curve we are going to take another point, say Q, and this point Q is at a distance of small h from this, so that this point is basically A plus h. So the coordinates of Q can be written as A plus h, f of A plus h. Likewise, let's also take a point here, say this is the point R, and here the coordinates, this point corresponds to A minus h on the x-axis. So coordinates of R would be A minus h, f of A minus h. Now h is a very small quantity, it is very close to 0, say it can be a small value like 0.1, it can still be smaller like 0.05. Whatever be the value of h, we mean to say that this distance is a small distance. Likewise, this distance is also a small distance. We are not mentioning that, we are not saying that these two values are exactly same. They can be different. This can be 0.05, this can be 0.1. So this is basically an expanded view of a graph. So now let us see here, if we join the points P and Q and extend it further like this, we obtain a secant. Alright, and we can find out from the point P, if we drop down a perpendicular here, say this is the point T, then we can easily find out here slope of the secant PQ. And we know slope of the secant or slope of any line is given using this formula y2 minus y1 upon x2 minus x1. Since we are referring to points P and Q, so these are values of x1 y1, x2 y2. So slope that ways can be written as f of a plus h minus fa upon a plus h minus a, that would give us h. So this is slope of PQ. Now let us move to a situation where this point Q is brought closer and closer to P till it is almost coincident with P. So I'll draw another graph here. This is graph of the same function. This is our function. Y is equal to fx. This is the point P that I have taken. Somewhere here is the point Q. Alright, initially we have drawn a secant passing through the points P and Q. Now in the next situation we are bringing this point Q closer and closer to P. See, if the point Q is suppose here, on joining PQ, this is the secant that is obtained. Alright, if we still bring Q closer to P, say Q is almost here, in that case we obtain a line that goes like this. This is the line. So whenever Q is very close to P, see here the black line indicates it's coming closer to P. It is still a secant. Alright, when the point Q is exactly here, the line becomes like this. Now you can see here in the figure that here the line becomes now a tangent. So that means we can write down here, whenever the point Q tends to point P, in that case the secant PQ tends to become a tangent at the point P. Now instead of saying Q tends to P, we can also write down H tends to 0. When H tends to 0, that means this distance here is reducing. This point is coming closer, 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 closer to the point A, and hence this distance, which is H, is almost becoming 0. That's what we are saying here. Instead of saying Q tends to P, we can also say H tends to 0. When this happens, the secant PQ is coincident with the tangent P, because both lines are coincident. So we can say here that the slope of the secant PQ is equal to the slope of the tangent. And the slope of PQ, this is the slope of PQ. F of A plus H minus FA upon H. This slope is obtained in this limiting condition. So when H tends to 0, this is the slope, and then this slope is equal to the slope of the tangent, and the slope of the tangent can now be expressed as derivative. So this is the left hand derivative that we have obtained. So what does a left hand derivative tell us? It tells us that we obtain a tangent when we are finding out, sorry, this is the right hand derivative. The point A is approached from the right hand side. The secant becomes a tangent, hence the slope of secant is equal to the slope of the tangent, and the two slopes are equal. The slope of tangent is given by this. We know this is the right hand derivative. Now that means we are talking of derivative. So this has to be derivative. That derivative we are representing as dy by dx, hence this becomes the slope of the tangent. So now let's move on to the next situation where Let us join the points PR. This is what we have joined, alright, and extending it further, this is the line that we obtain from the point R. If we drop down a perpendicular here, say this is point S, so I think you all can see this secant RP. So now let us find out here what is the slope of the secant RP. We are using coordinates of the points P and R, so P and R, and we can write it down as f of a minus h minus fa upon minus h. This is slope of RP. Again, look into this figure. The point R is carried closer to the point P. So let's come to this figure now. Here is the point R. Alright, R is coming closer and closer and closer to P. So when it comes here, you can see if R is suppose here at this point, this is the secant, right? And as this point comes closer and closer to P, this blue line is obtained. That means the same tangent is obtained. This is what we are going to write down here in a similar manner that we are writing this. So when the point R tends to P or when H tends to 0, once again we can write down that the secant RP now becomes the tangent at P, and hence their slopes would be equal. So straight away writing down, when H tends to 0, the slope of the secant, which is given by this, is equal to the derivative or the slope of the tangent, because this is the left hand derivative. So this derivative we are representing by dy by dx. This is how the left hand derivative comes into picture. Now look at these two cases. Here we are mentioning right hand derivative is dy by dx. The left hand derivative is also dy by dx. So both these derivatives are equal and hence the function is differentiable. According to the figure, what do we have? These were the two secants we had initially. Both the secants are reducing down to a tangent under specialized conditions. Whenever h tends to 0, secants become tangents, and in that case the slope of the tangent is given by these derivatives. You can also see in the figure that this blue line is the tangent. This is the angle which is made by the tangent. So whenever this angle is an acute angle, the slope of the tangent, that means the derivative is going to be a positive quantity. And in case this angle is an obtuse angle, in that case the slope of tangent, which is dy by dx, will be a negative quantity, because we have studied in earlier classes also that slope is also given by tan theta, and we know in the first quadrant tan is positive, in the second quadrant tan function will have a negative value. Okay, so this is how we have seen geometrically when we are differentiating a function at a point, algebraically when we are differentiating a function at a point. So geometrically what is happening at that point on the curve, a tangent can be drawn. Alright, so here in the definition we had mentioned a differentiable function at a point x is equal to a. So at this point two tangents can be drawn if these two tangents exactly coincide. That means we've drawn actually secants, but in a limiting situation both the secants coincide with the same tangent. In that case LHD is equal to RHD and the function is said to be differentiable function. Now let us see some examples of differentiable functions, special kinds of functions. So the first function that we are going to study is y is equal to x squared, and this you can make out is basically a parabola whose focus is on the positive y-axis. So the curve, it's a standard parabola, so the curve would be somewhat like this, passing through the origin. Alright, so here we are checking the differentiability of this function at the point, say, x is equal to 0. So the basic definition of the left-hand derivative. The left-hand derivative is limit h tends to 0, f of a minus h minus fa upon minus h. So where is this point A? This point A is basically equal to x. Alright, so we know our point is 0. So substituting here A as 0, we get f of minus h, f of 0 upon minus h. The functions f of minus h. So here it is minus h square minus 0 square upon minus h. Simplifying it further, we have here h square upon minus h, which is minus h, and by direct substitution this turns out to be a 0. You can see this is a finite real value, so LHD is 0. What is LHD? Slope of the tangent. Alright, so geometrically what is going to happen here? At the point x is equal to 0, there is a tangent whose slope is exactly equal to 0. If the slope of a tangent is 0, that means the slope is parallel to the x-axis. Now since this tangent is passing through x is equal to 0, so the x-axis itself is the tangent. So here I am going to draw a tangent which is passing through this like this. Although the figure, it does not seem to be coinciding with the x-axis, but you have to understand that this is coinciding with the x-axis. I am showing it this way so that it can be clearly seen. Okay, that's the left hand slope of the tangent when we are approaching this point from the left hand side. Next, let's find out the right hand derivative. So again, starting with the basic definition. This is it. Here again a is 0. So f of h minus f of 0 upon h. The function here is h square minus 0 square upon h. Further simplification gives us limit of h when h tends to 0, which is 0 here. So you can see here that the left hand derivative is equal to the right hand derivative. Both have finite values. That means this function y is equal to x square is differentiable at the point x is equal to 0. Now here in the graph, the blue line that you see is the slope of the tangent which we have obtained finding the left hand derivative. There is another tangent whose slope is again 0. When is this tangent obtained? When we are approaching the point 0 from the right hand side. So I am drawing the tangent like this. Now because the slope is 0, this tangent is also coincident with the x-axis. The figure simply illustrates that we have drawn two tangents. Both these tangents are coinciding with the x-axis. So you can see that we have got left hand derivative, right hand derivative, both are equal. Geometrically, what do we obtain? We obtain two tangents, both of them are coincident tangents, and in this case the tangents are actually the x-axis itself. Alright, so we have seen here that this function is differentiable. Let's explore one more function. Y is equal to modulus of x. And this also we shall be checking differentiability at a is equal to 0. So x-axis, here is the y-axis, and the modulus function can be drawn like this. So this is where we are checking the derivative differentiability of the function. So let's once again start with the left hand derivative. This is the basic definition of left hand derivative. Since a is 0, So f of minus h minus f of 0 upon minus h, and the function is the modulus function, so this will become modulus of minus h modulus of 0 upon minus h. Simplifying it further, numerator is h, denominator minus h, cancels to give you minus 1. Limit of a constant function is the constant itself. So that means the left hand derivative is minus 1. We'll see the graphical interpretation just now. Let's find out the right hand derivative. Limit h tends to 0, f of a plus h minus fa upon h. Our point of reference is 0, so it becomes f of h minus f of 0 upon h, and the function is modulus function. So we obtain here limit h tends to 0, modulus h is h upon positive h, which is equal to plus 1. So you can see here left hand right hand derivatives are not equal. The left hand derivative not equal to right hand derivative. Therefore the function y is equal to mod x is not differentiable at x is equal to 0. This is the algebraic process. Graphically what is happening? So let's move on to left hand derivative. No, let's start with right hand derivative. Right hand derivative is plus 1. That means the slope of the tangent is plus 1. And we have just seen that the slope is positive whenever the angle is acute. So that means when we are approaching this point from the right hand side, say the tangent obtained is this. This is the tangent. Alright, you can see the tangent is making an acute angle with the positive x-axis. So this is the tangent that's obtained whose slope is plus 1. Next, let's see here, left hand derivative, slope is minus 1. Slope is minus 1, that means tangent is making obtuse angle. So let that tangent be this. This is that tangent. You can see here this angle is, say, an acute angle, obtuse angle. So the slope is negative. Alright. Now in the figure it is clear that we are getting two tangents. Let's call this tangent T2, this is T1. So these two tangents do not coincide. The tangents do not coincide. So that means geometrically you are getting two different tangents. So whenever geometrically we get two different tangents, that means the function is not differentiable at that point. We have discussed two examples. Let's compare. Looking at this graph, we know it is graph of a continuous function. The graph of modulus function is also continuous. Alright. At some point on the graph of continuous function like this one, the function is differentiable. At some point of the graph, that means the continuous graph, in this case we see the function is not differentiable. So we get to know that if a function is continuous, it may not necessarily be differentiable also at some point. A function is continuous, it may be differentiable, it may not be differentiable. So here you are asked a 1-mark question in the board exam. Give an example of a function which is continuous but not differentiable at some point. This is that question. This is the answer basically. Modulus function is a function which is continuous throughout its domain, but then it is not differentiable at the point 0. Let's change the modulus function. If the modulus function is this, then we know this function is continuous throughout its domain, but then the function is not differentiable at the point x is equal to 1. Alright, let's take another example. Y is equal to mod of x plus 2. This is because it's a modulus function. The function is continuous throughout its domain, but then the function is not differentiable at the point x is equal to minus 2. So you can easily find out at which point the function is not differentiable. Equate this to 0, you get value of x. Alright, so here when you put x is equal to 0, the function was not differentiable at x is equal to 0. So this is an important 1-mark question. We shall see two more such examples. So the third example that we are considering is y is equal to x to the power 1 by 3, and here again we are checking the differentiability of the function at some point which is 0. So let's draw the graph also. So here when you put in various values of x and find out corresponding y, the graph would be somewhat like this. This is the graph. Okay. So now let's find out here the left hand derivative. Here we know the point of concentration is 0. So f of minus h minus f of 0 upon minus h. The function is x to the power 1 by 3. So this will be minus h to the power 1 by 3 minus 0 upon minus h. So using laws of exponents, this can be written as minus h to the power 1 by 3 minus 1, which turns out to be minus h to the power minus 2 by 3. So here if you think you directly substitute h is equal to 0 and it turns out to be 0, then let's wait, because the power is negative. First of all, let's make the power positive, writing it down like this. Now here when we substitute h is equal to 0, this limit basically is not defined. Alright, the limit of this function is not defined. Next, let's find out right hand derivative. Once again, our point of concentration is 0, so it becomes f of h minus f of 0 upon h, and the function is h to the power 1 by 3 minus 0 to the power 1 by 3. So here again what we get is, using laws of exponents, it's once again h to the power minus 2 by 3. So we'll ensure that the power of the function is positive like this. Now when we directly substitute h is equal to 0, this is also not defined. So here there should be no confusion that the left hand derivative is not defined, right hand derivative is not defined. That means these two derivatives are equal and hence the function is differentiable. We have mentioned in the definition of differentiable function that the limit has to exist finitely. When we are saying it is not defined, that means the limit does not exist. Alright, so here we can write down here that since LHD and RHD are not defined, therefore this function y is equal to x to the power 1 by 3 is not differentiable at the point x is equal to 0. Okay, now graphically what is happening? See, we are saying left hand derivative is not defined. Left hand derivative means slope of a tangent, right? And the tangent, the slope of the tangent is not defined. That means what is the angle that the tangent is making with the positive x-axis? It is making an angle of 90 degree. Tan of 90 degree is not defined. So here, since our point of consideration is origin, that means the tangent is passing through origin and then it is coinciding with the y-axis. So here I'm going to draw a dotted line like this. This dotted line basically indicates the tangent which is coinciding actually with the y-axis. I'm drawing it so that you can see it. It is actually coinciding with the y-axis. Likewise, RHD, again it is not defined, so it is the same tangent here. Now since the tangents are coinciding, so LHD is equal to RHD, but then the function is still not differentiable because we need to have the left hand and right hand derivatives to exist finitely. That means these values have to be real numbers. Okay, let's see one more example. let us consider the greatest integer function, say at a point x is equal to 1, some integral value. X-axis, the y-axis, these are some points 0, 1, 2, 3 and so on. If we plot the graph, we know from 0 to 1 the graph would be somewhat like this, 0 included, this is not included. From 1 to 2 the value is equal to 1, so the graph would be like this, and at 2 the value is 2, so it is like this, a step size. Alright, so our point of consideration is 1. As you can see here, the function is not continuous at 1 because there is a jump from here to here. So obviously function will not be differentiable, but let's check. So left hand derivative, the left hand derivative, limit h tends to 0 and f of a minus h minus fa upon minus h. Now this time our point of consideration is 1, so f of 1 minus h minus f1 upon minus h. So this is greatest integer value of 1 minus h, and this can also be written as greatest integer value of 1 minus h would be 0. This is an integer, so it remains this minus h. Now here you know when you substitute h is equal to 0, again this left hand derivative is basically not defined. Okay, so left hand derivative not defined. Let's see the right hand derivative. Limit h tends to 0, f of a plus h minus fa upon positive h. So here I am directly writing down, this would be greatest integer value of 1 plus h minus 1 upon h, and then the greatest integer value of 1 plus h would be 1 minus 1 upon h. Now here you have to clearly understand here that the numerator is 0. If the numerator is 0, we do not substitute h as 0, we say the limit is 0. Okay, so it is not 0 upon 0 indeterminate form. So this is what you have to remember. So here we again notice that LHD is not equal to RHD. Therefore, the greatest integer function is not differentiable at x is equal to 1. At any integral value, the function will not be differentiable. So now let us see where are the tangents. So let's look at the tangents here, starting with RHD. The right hand derivative is 0 at the point x is equal to 1. That means the tangent that is passing through x is equal to 1 has slope 0, and we know whenever the slope of tangent is 0, it's a line which is parallel to x-axis, and in this case it will be the x-axis itself. So this is the tangent, let's call it T2. Alright, now the left hand derivative, tangent is not defined, the slope is not defined. The slope of a tangent is not defined whenever the tangent makes an angle of 90 degree with the positive x-axis. Where is the tangent drawn? At the point 1. So that means at 1, the tangent is parallel to the y-axis like this, tangent T1, making an angle of 90 degrees with the positive x-axis. So the figure clearly states that the two tangents are not coincident, the two tangents are not unique. So geometrically also the function, the greatest integer function is not differentiable at the point x is equal to 1.